Welcome to another episode of Dominic Does DIY. As always, like, subscribe, and comment down below if you find this entertaining or useful. Also, if there's anything you'd like to see or explained, let me know in the comments down below. So let's go ahead and get it started. Today you found out over the weekend an entire department in a satellite office got shut down. It was a small engineering group, but with them gone, their projects become your projects. However, due to a bunch of IT nonsense, getting information is almost impossible. They won't let you download the data without some form, sign in triplicate, and having to wait a couple weeks to get what may or may not be the files you need, depending on what they saved and where it is found. Instead, you decide to just go down and pick up everything yourself. So you box up everything that they were working on, and you're just going to bring it back to figure it out. From what you were told, their project is a controller that is to detect when an external battery pack is connected. You take a look at their main project and review the PCBA, and you can make out some of their ICs on it and trace it out. It looks like they have a single cell lithium powering the PCBA, and this single cell powers the main control board. They are using a small 8-pin micro to run some controls like an LED indicator and some solid state switches. The problem with the board is they smoked the micro. You are curious on how this happens, and you investigate further and trace out the rest of the circuit to determine what the issue could be. After spending some time, you have traced out the schematic and found the circuit has the following functions. Stack detect, which checks for if the pack is inserted or not. LED, which allows for the user to know power is detected or something, not quite sure yet. VBAT ADC and VBAT ADC enable, which checks the stack battery voltage with an analog input. And main power enable, which allows the stack voltage to power the system. In the box of stuff you recovered, you did find some notes regarding the firmware and the pins. Stack detect is a digital input and it is connected to an interrupt pin. LED is a digital output. VBAT ADC is an analog input. Main power enable is a digital output. And VBAT ADC enable is a digital output. Along with this, there are some additional notes that says, when the stack is detected, enable system power. If the stack battery voltage drops below 15 volts, disable system power. And if system power is enabled, light the LED. You take this information to the firmware gal who looks at it and decides it is easy enough. She even had some of the micro in her stash so she can program it and give it to you. Before she completes the firmware though, we have to see if there is a hardware issue that caused the micro to blow up. After you remove the micro, you measure the VCC rail to make sure there isn't a short on the board. After applying power, you start simulating GPIO and checking levels. Everything seems adequate at the hardware level. A little bit later, the firmware gal comes in and hands you a couple programmed micros just in case. You plug in a single cell battery to power the rail after installing the micro, and nothing extraordinary happens. You check the outputs from the micro and they are as expected. So you go ahead and connect in one of the 5-cell packs that were in the box. And bam! The micro takes a hit. Now you did it. Good thing she gave you more than one micro. Now we have to figure out what went wrong. You measure the single cell battery and it is at 3 volts. You measure the 5-cell battery and it measures 18.5 volts. Nothing out of the ordinary with those voltage levels. You look at the circuit drawing again, and after studying it for a little bit, you see what the problem is, and now need to consider how it is we can fix it, or at least make this PCBA work for testing. So the question is, what is the issue that was found in the circuit, and how can we fix it? Pause the video now if you would like to examine and solve the problem yourself, or continue watching for the solution. With this particular problem, there could be multiple solutions, and I will only show one. If you have another, please list it in the comments down below. I can think of a few methods given the open-endedness of my question. First thing, we have to make some assumptions here on the micro, which really are not far off in reality here, but I will list them just to make you aware. 1. Micros have an operating range. We are going to assume we did not violate that, considering when we plugged in the single cell battery, nothing happened. It was only after the 5-cell battery was attached we had an issue. 2. Micropins have limits based on VCC. VIH has to be a minimum of 0.8 VCC in order to detect a high. VIL has to be 0.3 volts VCC in order to detect a low. And the absolute maximum voltage level on a pin is VCC plus 0.3 volts. We have to kind of think how they may have thought. As I have mentioned before, we always have to consider tolerances and stack up. Clearly, the team that was let go must not have taken something into consideration here. I went ahead and made a spreadsheet to facilitate this. So using our spreadsheet, we know our V-stack divider is this right over here. So R8 and R9, and R8 is 165K, R9 is 36K. We also know that our VBAT was 3 volts, and our stack voltage was 18.5 volts. Just looking at this, we can see our issue. Our micro is at 3 volts, and at 18.5 volts on the stack, we have 3.31 volts on the pin. This exceeds our standard VCC plus 0.3 volt operating range and exceeds the limit, causing damage to the pin and the micro. The guys on the other team weren't newbies though, so where did they go wrong? Well, let's put the VBAT at 3.7 volt nominal voltage. And you can see here, we can trigger, no problem. At 3.7 volts, the GPIO is well below the 3.31 volts is well below the 3.7 volts plus 0.3, so we don't have a problem there. And the GPIO 3.31 volts is greater than our input voltage high limit of 2.59 volts. So there's no problem here when the stack voltage is at 3.7 volts. And even if we change the stack voltage, let's say we go down to 3 volts per cell, because remember we're going to shut down at 15 volts anyway, you can see that our GPIO pin, our input, is 2.69, which is still above our input high voltage level, so we will trigger. And if we go all the way up to 4.2 volts per cell, which gives us a stack voltage of 21 volts, it puts our GPIO at 3.76, which is above our input high level of 2.59. And it is still, even though it is above our VCC, our battery voltage, it's not above it into catastrophic range, right? Because we're allowed VCC plus 0.3 volts. So we are below that. We could go up all the way to 4 volts and remain safe. So this is where their problem lied. When they did their calculations, they confirmed that their voltage divider would work with the range of the stack, and so that they would be able to operate correctly, but they neglected to consider the effects the battery has of being VCC on the system. So looking at our calculator, let's consider the two extremes of the supply voltage. That is at 3 volts and 4.2 volts. The problem we have is that when the battery is fully charged at 4.2 volts, our VIH is 2.94 volts. And when the battery is at low voltage at 3 volts, the maximum pin voltage that we can accept is 3.3 volts. So the swing that we have is only that 3.3 volts minus the 2.94 volts, which is 0.36 volts of a swing on that voltage divider. But if you look down here at the stack voltage, it can do the same thing, right? Each cell can be 3 to 4.2. We have 5 of them in series. And so the stack voltage can go anywhere from 15 to 21 volts. Well, with our divider we have right there, you can see that the voltage swing on the stack voltage is 2.69 volts all the way to 3.76 volts, which is on the stack a swing of 1.1 volts. So there's no way we can use a simple voltage divider here. And just so you can see what I mean, is we would have to make the GPIO trigger under worst case. That is, when our stack voltage is low, right here, when this is low at 15 volts, and our battery is fully charged, our voltage divider still got to be able to trigger. So the only way we can do that is we got to throw a 41K resistor, because right now, this battery won't trigger, right? Our VIH on a fully charged battery is 2.94 volts, but our GPIO from the voltage divider is only 2.69. So there's no guarantee that we will trigger. So the only way we can guarantee a trigger is we got to go to 41 kiloohms on R9, which then makes us trigger at 2.99 volts. Unfortunately, now we have to consider, okay, well, what happens when, and that meets spec, right? But now we got to consider what happens then when our stack voltage goes fully charged at 4.2 volts. Now we got 21, and our battery here is at low voltage, right? So as you can see, we will have a 4.18 volt on the pin, but we can only accept 3.3 volts. So there's no way we can use a voltage divider. We need a different method. And like I said, there are many solutions, but my solution that I chose here is a pretty expensive one. I chose to use an analog comparator because what we need to do is be able to work with this swinging voltage, but we need to be able to tighten it down and make it less variable, right? We got to be able to do something about this. So looking at the spreadsheet for the analog comparator, we have two voltage dividers. We have R3 and R4 here for the stack, and we have R1 and R2 for the battery. So that's what we have right here, R1, R2 for the battery, and R3 and R4 for the stack. As we know in a comparator, it'll output high when N plus is greater than N minus, and it'll output low when N minus is greater than N plus. So our N minus is being controlled by the battery voltage divider. And so I just picked some values right here, 165 and 50. And so basically it gives us 0.7 volts. And I want to pull that down to give me some headroom. Because remember, with the other one, our problem was in the fact of when we were at high voltage, that trigger point was so high that it caused us to basically blow up, right? It lowered that range, right? It only gave us 34, 36, 360 millivolts of headroom. Whereas over here, because I've lowered this, now when I go to 4.2 volts, I got 0.98, let's just call it 1 volt, but that gives me 2 volts of swing that I can have on the stack voltage, right? Because I'm still bound by the same rules. At low voltage over here, I still have to be, my N plus still has to be greater than my N minus in order to trigger. So at 165 and 15, I've got a low battery cell, stack voltage 15. My N plus is going to be 1.25 volts. That is greater than my N minus, so I will output high. I will trigger even when I got a full stack battery voltage. And when my stack voltage goes to fully charged, my N plus becomes 1.75, which is still well within all the specs on the range of the battery. So it'll trigger because N plus will always be greater than N minus. But at 1.7 volts, I don't violate the analog comparator's VCC value, which means no chip will be harmed in this circuit. And so we got that going for us with the analog comparator. It allows those voltage swings to be able to be tightened up and to play a little bit more with them. And the nice thing about the analog comparator is because it is an digital output, right? It's either going to be it's rail to rail. So it'll either be VCC or it'll be ground. It'll feed, and it's being fed by the same voltage that our micro is. We don't have any voltage variances there. It'll work just fine. So yeah, that's it. That was my solution, is the analog comparator. As I said, there's a couple other solutions. So I can think of a couple solutions in the hardware world, just off the top of my head, to solve this besides the comparator. So whatever you come up with, go ahead and write it down in the comments. There's also a solution where you can kind of kick the can back to the firmware and make it her problem. I just went with this way because it's easy, because she did give us extra chips. So she wouldn't have to reprogram it. I can just put one of those old chips on, scab this thing onto the board, give it a shot, and decide what to do from that point on. But there is a firmware solution to this too, if you were paying attention to the schematic. I did leave a firmware option open. But that's all I have this time. So thanks for watching, and I hope you enjoyed the video. And thanks again to all who have subscribed. We're up to 60. So maybe by next weekend, I can get another 40 and make it to 100. So subscribe if you haven't, and share the video with your friends. And I will see you next time. Have a good one.